Okay, welcome back to my next video lecture. Our topic is still kinematics, but today we finally move from the description of objects with a constant velocity to motions with, where the derivative of v with respect to t is not zero anymore, which means that the object accelerates or is accelerating. As we have seen in the very beginning, the definition of velocity is simply the change of position divided by the elapsed time for this change or during this change. If the speed is constant, we can just write v equal delta s over delta t. If it is not constant, I mean if the velocity is not constant and additionally a three-dimensional vector, then we have to calculate the derivative as shown here. v equals dr, d vector r over dt, or shortly r dot. The main idea of describing accelerations now is to use the same definition, but simply replace displacement or distance with velocity and velocity with acceleration. This results in the definition as shown here. A is equal to v dv over the acceleration is equal to dv over dt, or shortly written as v dot. If the derivative is zero there, then simply no acceleration takes place because the velocity does not change. If the derivative is constant, then the acceleration does not vary in time, is also therefore constant. For the time being, we just stick to cases where the acceleration is constant, just because there are many examples in the near future where this condition is mostly fulfilled. For example, if you press the acceleration pedal of a car, then the acceleration is also constant within a certain time window. Now we take a look at the so-called acceleration time diagram for a constant acceleration, or shortly a t diagram, as illustrated here. Because a is constant, the result is just a horizontal line, similar to the vt diagram for a constant velocity. Switching now to a vt diagram for a constant acceleration, as presented here, a velocity time diagram, we get a linear dependency between v and t, just because v is again interpreted as the area under the graph in the at diagram. This we have seen already in the last video. Therefore, we can simply write v is equal to a times t, as shown here. In this graph, the slope, which is equal to the acceleration, turns out to be delta v over delta t and not delta s over delta t as in an st diagram. Until now we have seen that the correlation between velocity and acceleration is equal to the one we have seen before for displacement and velocity. If you still feel a little bit unfamiliar with these terms or with all of that, I suggest to go back to the previous videos that I have made before and watch them very carefully again, because now we will use this obtained information to calculate the distance the distance with a constant acceleration. For that we have to calculate now the area under the graph in the vt diagram that I have shown before, and this is a triangular shape. The area of a triangle is simply, as you might know, 1/2 of the base of the triangle times the height of the triangle. The base in this diagram, which I have shown before, is then simply associated with the time interval t, whereas the height is given by the velocity of the object at that time. So therefore, it follows for constant acceleration, s is equal to 1/2 times v times t. Now in the next step we insert this correlation into the formula s is equal to v times t that I have introduced already in the last video. Then finally we obtain the correlation between s and t as shown here, which is simply s equal to 1/2 a t square. And this formula now says that we obtain a quadratic correlation between the displacement and the time if the acceleration is constant. And this is very important because this result is somehow new. It is now the first time that we don't have a linear dependency between a quantity and time. And also the factor 1/2 comes additionally into this formula, which is simply a result of the non-constant and linear increasing velocity. Now I want to show you that with the help of integration, we would obtain the same result. First we have to integrate over a from a given start point, let's assume at the time 0, to the end point of an arbitrary time t. I have written here in this equation dt prime just in order to differentiate between the integration constant t and the upper integration limit, which is also t. The result is as expected, and is shown here, a times t for the velocity. For the second integration, in order to obtain s, we have to integrate over the previous result v times t from 0 to t again, and obtain finally s equals to 1/2 a t square if we apply all rules of integration correctly. And this result is, as I said, equivalent to the previously obtained result for the displacement, and this makes also fully sense because the integration process is basically just the calculation of the area under the graph, and therefore we should receive the triangle area again after integrating. We could also go the other way around and start with the formula s is equal to 1/2 a t square. In order to calculate the speed or the velocity, we have to calculate the derivative, ds over dt, v equals ds over dt. This results then in v equal to a times t, after applying all the rules of differentiation. In the second derivative, dv over dt, the variable t drops and only a remains, which is therefore then defined as the acceleration. Finally, we can also take a look at the ST diagram for a constant acceleration, and this is shown here. As you can see, the resulting graph is or has a shape of a parabola. The left side of that parabola for negative times has been removed just because of its unphysical nature. Yeah? But this is just to show again the quadratic correlation between S and T. On the last slide, I want to briefly summarize the result of this video and also the last videos by revising again the different diagram types about which we have learned how to use them. So if an object, in the first row, if an object doesn't move, the position of the object remains constant. This I have explained in the very beginning already. And the line of the ST diagram is completely horizontal. The derivative of s is then in the second diagram 0, which means the velocity and the acceleration must be also 0. If in the next row the object travels with a constant speed, the ST diagram shows a straight line, whereas the VT diagram is constant and a is again 0, so there is no acceleration taking place. In the last row we come to the diagrams where a is constant, and this we just learned in this video. We have again the parabolic shape of the graph in the ST diagram, a straight line in the VT diagram because of the derivative, and the horizontal line in the AT diagram as explained a few minutes before. Because I introduced now a complete new quantity, physical quantity, which is called acceleration, I want to stop the video here and continue in the next one with calculating some more examples and also to go a little bit deeper into this topic, when we will also see that things which fall on the Earth's surface have also a constant acceleration. Please stay tuned. I will try to record it as soon as possible. For those who have not done it so far, please subscribe to this channel. And remember, physics matters.